Welcome to an exploration of one of nature's most fundamental and fascinating forces. Gravity is the invisible architect of our cosmos, orchestrating the dance of planets, binding galaxies together, and keeping our feet planted firmly on the ground. From the moment Isaac Newton observed an apple falling from a tree to Einstein's revolutionary reimagining of spacetime itself, humanity's quest to understand gravity has driven some of our greatest scientific breakthroughs. This study guide will take you on a journey through the principles, mathematics, and real-world applications of gravitational force, building your understanding from basic concepts to the cutting edge of modern physics. Gravity is the fundamental force of attraction that acts between all objects possessing mass or energy in the universe. It is one of the four fundamental forces of nature, alongside electromagnetism, the strong nuclear force, and the weak nuclear force. What makes gravity unique and somewhat mysterious is that it governs the greatest structures in our cosmos, from planetary systems to galaxy clusters spanning billions of light years. It is paradoxically the weakest of all fundamental forces. In 1687, Sir Isaac Newton published his groundbreaking Philosophiae Naturalis Principia Mathematica, which introduced the law of universal gravitation. This revolutionary insight proposed that masses in the universe attract each other with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This elegant mathematical relationship explained the orbits of celestial bodies, enabling both why objects fall to Earth and why planets orbit the Sun. The relationship between Earth and the Moon provides a perfect example of gravity in action. The Moon orbits Earth not only because it's moving in a perfect circle, but also because of gravitational forces acting toward Earth, while the Moon's forward motion exactly balances Earth's gravitational pull. Both bodies actually orbit around their common center of mass, called the barycenter, which lies about 4,700 kilometers from Earth's center, inside Earth but not at its center. This pulling and pushing also cause tidal effects, with the Moon causing bulges on the sides facing toward and away from the Moon. Rather than thinking of gravity as a direct force between distant objects, it is more useful to conceptualize a gravitational field, an invisible influence that surrounds any mass and affects other masses within it. Every object with mass creates a gravitational field and extends infinitely in all directions, though its strength diminishes with distance according to the inverse square law. The gravitational field strength, denoted g, at any point in space measures the force that would act on an object with mass placed at that location. It is expressed in newtons per kilogram, n per kilogram, or meters per second squared, meter per square second, which represents the acceleration a falling object would experience due to gravity. The difference in gravitational field strength between Earth and the Moon results in a noticeable difference in weight. On Earth, the gravitational field strength is approximately 9.8 n per kilogram, meaning a person weighing 70 kg would experience a force of about 686 n. On the Moon, the gravitational field strength is only about 1.6 n per kilogram, so the same person would weigh significantly less, experiencing a force of about 112 n. The experimental investigation of gravity has evolved from Newton's observations of pendulums and planetary orbits to extraordinarily precise modern measurements using lasers, satellites, and atom interferometers. Each generation has contributed to a deeper understanding of gravity, leading to ever greater accuracy. Newton used pendulums to show gravitational acceleration was independent of mass. He analyzed planetary data from Kepler to develop his law of universal gravitation. Cavendish used a torsion balance to measure the first measurement of g, while modern experiments use laser interferometry to detect gravitational waves. In 1915, Albert Einstein revolutionized our understanding of gravity with his theory of general relativity. Rather than viewing gravity as a force that mysteriously acts across empty space, Einstein revealed that gravity is the curvature of spacetime itself caused by mass and energy. Massive objects literally warp the fabric of space and time, and other objects follow the straightest possible paths through this curved geometry, paths we perceive as orbits or falling motion. Gravity is the cosmic sculptor that has shaped every structure in our universe, from the smallest asteroids to the largest galaxy superclusters spanning hundreds of millions of light years. Its infinite range and cumulative effect means that gravity becomes the dominant force at astronomical scales, even while it remains the weakest force at the quantum level. Gravity affects every aspect of our lives, from guiding planets, galaxies, and cosmic phenomena to everyday applications like satellite technology, space missions, and our exploration of the cosmos. By studying gravity, we gain insights into the universe's fundamental architecture and predict future cosmic events. This understanding is crucial for advancing technology and exploring the universe's mysteries.